Hey everyone, Professor Dustin here, and this video is going to be a quick solution to this one-dimensional elastic collision problem where I have a object of mass m and velocity v0 colliding with a object of mass 3m and a velocity of 1/2 v0 traveling in the other direction. So in these kinds of problems we have momentum conservation, so the initial momentum is going to be equal to the final momentum. Let me write out that in just one dimension, in just the x direction, and now let's also put in the m's and v's for the total momentum combining both objects. It looks like that, and you can see what I've done is I put in v0 for the initial velocity and then the initial mass, the mass of the first one rather. I put a negative sign in to indicate that this one is going backwards. These guys are components now, so I have to put in signs if I'm going to indicate directions. 3 times the mass is the second one, half the initial velocity, and then the final two speeds, actually these are components in the x direction, I've left as both positive, saying that, well, they might end up being negative in the end, but I'm not going to assume anything about their sign at this point. So we also have a conservation of energy in these problems because it's an elastic collision. Of course, we're only concerned about the kinetic energy of the entire system, and so we write it like that. Putting in the m's and v's, we get the following expression, where the kinetic energy of each is 1/2 mv squared, so I put in the 3m there and then the 1/2 v0 there. Of course, this is positive because we are just going to be adding up the energies of each of the particles, and then we have these unknown v's here as well on the right-hand side. So I'm going to have to combine these two equations. I have two unknowns, v1 prime, v2 prime. Clearly what I'm going to do is try to eliminate the v's by solving the momentum equation first and then plugging into the kinetic energy equation, because that's going to be easier than trying to take a square root to solve for v1, for instance. Before doing that, I'm going to simplify the energy equation a little bit. I have a 1/2 in every term, and I also have an m in every term, so I'm going to be able to cancel that out. So let me write that first. That gets me that 3/4 comes from the 3 times 1/2 squared, 3 times a quarter. And you can actually see that we can combine stuff on this side too. This is 4/4 plus 3/4, so that would be 7/4 on that side. So that's going to be our energy equation. Oh, I forgot the squared right there. Okay, so now let's go back to the momentum equation and actually perform the solution. So I think what I'll do, looking here, it doesn't look like there's going to be any real difference between solving for v1 prime or v2 prime. So let's go to momentum. Let's solve for v1 prime. Well, be careful. Don't forget the 3 in front of the v2. That comes from this 3 right there. So just checking that. That is going to be divided by m, that v0, 3m over 2 divided by the m is going to be minus 3 over 2 v0. Subtracting the 3 v2 is going to get that. Okay, but now I can actually combine these two terms together. That's going to be a minus 1/2 v0 minus 3 v2 prime. Okay, so now I'm ready to take this, that v1, and put it into the conservation of energy equation right there. Looks like that, and now I have to distribute the quadratic of the squared there through this term, so that's going to give me this term squared, and then 2 times the cross term between those two. So there's just the result of that. 1/2 a quarter squared, that 3v2 prime becomes 9v2 prime squared, and then the cross term is 3 times 1/2. The minus signs cancel to give positive. 3 times 1/2 is 3/2 times 2, because there's 2 of them, just gives me 3, and then a v0 times v2 prime. And then the rest of the equation just follows along. So now I've got to collect like terms. We can see we are going to get a quadratic equation because the v0 squared terms do not cancel there and there. That's a 7. So we're going to collect the v2 prime squared terms together, put the linear terms together, and put the terms with no v2 prime squared together. We get something that looks like that. Notice this 3/2 came because I have a 1/4 minus 7/4. That's 6/4 or minus 6/4 when I move this guy over, and then that 6/4 becomes 3/2. So a quadratic equation with the variables a is 12, b is 3v0, and c is minus 3/2 v0 squared. Now, we can't go to like Wolfram or whatever. Actually, we could probably plug this into Wolfram, but without numbers, quadratic equation is a little bit easier to solve just by straight up writing out the variables. So that's what I'm going to do next. I will go to a new slide, I think. All right, so there's the quadratic equation I'm going to solve. Remember, minus b plus or minus square root of b squared minus 4ac over 2a. Doing that out. You can see that I get kind of a complicated thing just because of what's in here, but we can work that out pretty easily. 3 times 4 is 12. 12 times 12 is 144 divided by 2. 144 divided by 2 is 72. And then we have negative signs here, so that become positive. Okay, so that's a 9v naught squared plus 72v naught squared. That's nice because that 72 plus 9 is an 81, and I can actually take the square root of that. So that's going to be the square root of 81v naught squared. That's 9v naught. So we get two solutions, one related to the plus sign, one related to the minus sign. The plus sign is going to give me 6/24. Of course, 6/24 is just going to be 1/4. And the negative sign is going to give me minus 12/24, and of course 12/24 is just a half. So I have a positive 1/4 v naught and a minus 1/4 v naught are the two possible solutions. So now that's just for the velocity of the larger mass. In one case, it can go in the same direction that they were started, in the positive direction, so going backwards, it gets shot backwards away from the collision. On the other hand, it could also end up going to the left in the same direction that it was going originally, just in the same exact speed, actually, minus 1/2 v naught. So that's a little bit strange. That means that this velocity doesn't change at all, so that's likely the no collision case. So we're going to plug these numbers back into the other equation for v1 prime to find out, but my guess is that this is the no collision case because the velocity is actually unchanged. So looking back at the other slide, the expression for v1 prime was minus 1/2 v naught minus 3. Oh, that's a v2, excuse me. So let's do that first case, which I suspect is a non-collision, and plug in the minus 1/2 v naught. Okay, so that puts that minus 1/2 v naught there. This is going to be a positive 3/2 v naught. A minus 1/2, positive 3/2 gets me a positive v naught. And of course, that is the no collision case, because that's the case when the initial velocity for the first one is unchanged because of the collision. So that was indeed the no collision case. Now let's do the second situation. When the large mass bounces backwards away from the collision at 1/4 the original small mass's speed. That looks like that. So we have a minus 1/2 and then a minus 3/4. So that is a minus 5/4 v naught. So the other collision is it started going that way at v naught initially, but it actually turns around and goes backwards at minus 5/4 v naught is the final speed. And of course, what's happening in that case is that initially this larger mass was going 1/2, but now that larger mass is actually traveling in the positive direction with 1/4 v naught. So it's slowed down in speed, of course, but it's going in a different direction. It's changed direction because of the collision. Okay, that's it. So that has been a solution to this relatively simple elastic collision problem, but of course the fact that I had to use the quadratic equation to get the solution made it a little bit tricky, but it's not so bad because it ended up that the square root was relatively easy to take. We got two reasonable answers for the velocity of the second mass, and then we could easily plug them in to find the velocity of the first mass in the two different collision scenarios. Okay, great. Thanks everyone for watching. Hope this has been helpful, and I will see you all later.